Hello, my name is Sadie Coffin, and today I'm going to be talking about the Poynting vector and spectral line broadening in stellar atmospheres. Today I'm going to discuss the Poynting vector and its relationship to the power emitted by an accelerating charge into a given solid angle, with the goal of describing how to calculate the total power emitted by an accelerating charge. Part 2 of today's discussion will be discussing a few selected line broadening mechanisms in a stellar atmosphere and their significance in stellar analysis. Starting with the Poynting vector. A few important terms to note. An accelerating point charge radiates and loses energy, and it creates an external electric field that exerts an influence on other nearby particles. We can describe the power, which is an expression of dipole radiation, by starting with definitions of the radiation fields and energy flux, which can also be described as the Poynting vector. The radiation field here is described in terms of the angle theta between the acceleration direction and the line of sight. The Poynting vector describes an instantaneous energy flux, or radiated energy per time per area. We can find the total power emitted by integrating over the surface of a sphere, which provides a multiplication factor to the energy flux, and we end up with the Larmor formula for a non-relativistic acceleration charge. In order to talk about the Poynting vector, we need to talk a little bit about electromagnetic fields. The Poynting vector describes the rate of flow of energy for an accelerating charge. If we recall, electromagnetic fields created by accelerating charges are oriented perpendicularly to each other and to the direction of propagation. The magnitude of the Poynting vector is simply the power per unit area, and the direction is the direction of the wave propagation. Now that we've defined it, we can see how the Poynting vector can be determined from the cross product of the electric and magnetic fields, and therefore will be perpendicular to both. The size of the Poynting vector at any moment, that value of power per area, is found using the magnitude of electric field multiplied by the magnitude of the magnetic field. The direction is found using the right-hand rule to determine direction of propagation. And the Poynting vector is kind of like a measure of intensity with units of 1 over area. The vector describes the flow of energy, or the flux, and represents key information related to the radiation from a moving charge. But because of the Larmor formula, we're also able to calculate power through these basic steps. Returning to one of our original objectives, we wanted to relate the Poynting vector to quantities like the instantaneous power radiated by an accelerated charge. This graphic on the right shows how we move from the Poynting vector, or energy flux, to a quantity in terms of solid angle. The two are very similar and closely related properties. While energy flux describes how a field passes through an area, we can multiply by r squared to instead think about flux through a solid angle and take advantage of the written conversion factor. The total emitted power by an accelerated charge can be found in a similar way in one further step. We just have an additional task of integrating over solid angle to eliminate that dependence. And we are left with energy per unit time, which are the units of power. Electromagnetic waves carry energy and can transfer it to surfaces that light falls onto at a rate that's expressed by the Poynting vector. So in conclusion, the pointing vector provides us with magnitude and direction of the flow of energy, and it plays a crucial role in solving for the total radiated power or the flux through a given solid angle. Moving on to talk about line broadening mechanisms. Spectral line broadening refers to the effect when emission or absorption features, which under ideal conditions would be a narrow line at one discrete energy, or equivalent wavelength or equivalent frequency, as we recall the linear relationship between energy and frequency, and inverse relationship between energy and wavelength using Planck's constant. But in practice, these clean lines are often smeared to become broader features on a spectrum. This effect most often results either from a rotating cloud or a cloud that's really hot. Atoms moving around with random motions will have some moving toward and some particles moving away from the observer, causing red and blue shift effects from our perspective in the photons that reach us. So we can expect to look for both rotation and motion and temperature being the factors in these mechanisms. We will look at 4 different mechanisms to go over today: natural broadening, Doppler broadening, Stark broadening, and rotational broadening. The first 2 don't involve bulk relative motion of particles, that's natural broadening and Doppler broadening, but the second 2 do involve bulk motion. Starting with natural broadening. Natural broadening arises from the Heisenberg uncertainty principle, and it relates uncertainty in frequency to uncertainty in time. Therefore, we can see how a short lifetime leads to a large uncertainty and a broader emission line. A longer lifetime would lead to a smaller uncertainty and a narrower emission line. The shape of this emission line broadening is called a Lorentzian profile. The broad wings on either side come to a narrower core at the peak. Now, there are also other forms of broadening, such as the Stark effect, or Stark broadening. The Stark broadening effect is just like the Zeeman effect, but for electric fields instead of magnetic fields. If we recall from our earlier discussion about the Poynting vector, an accelerating charge creates an external electric field that exerts an influence on other nearby particles. The Stark effect is a broadening mechanism where allowed atomic energy levels are further split up and electrons have a broader range of energy states that they can occupy, as you can see in the bottom right, which is an example of the Zeeman effect, which is applied by a magnetic field instead of an electric field. In spectra with Stark broadening in play, the degree of broadening depends on the density of atoms in the surrounding area. A higher density leads to more broadening, which is usually found in main sequence stars and in dwarf stars, and a lower density means less broadening will take place, which is seen more in the cases of giants and supergiants. On the left, in the figure from a 2014 paper, you can see the spectra have a Stark width that varies with density, a quantity which is represented by the legend in the top right. Density increases as we go down, and you can see that the strongest broadening effect on the plot corresponds to the highest density value. The next broadening effect that we can look at is Doppler broadening. This is the first of the bulk motion broadening effects. On the left, it is compared with the Stark effect for magnetic fields, the Zeeman effect. And you can see how both mechanisms spread out the emission lines in a similar way. In the atmosphere of a star, the thermal energy of atoms gives them random velocities, and if they travel radially away or toward us, their light becomes slightly red-shifted or blue-shifted, and we can detect those red and blue shifts when we take an average of the spectra and we observe these smeared out energy values instead of one clean energy value. This mechanism looks different than natural broadening, and it has a Gaussian shaped profile instead of Lorentzian. We can also look at rotational broadening effects, where similar to the Doppler shift, but instead of random motions and velocities, the variation here in energy comes from atoms in different spots along the surface of a rotating body, which you can see on the left. If you know the period of this rotation, you can solve for rotational velocity and inclination, and we will have everything we need to find these useful quantities. This profile is again shaped differently than the previous ones, and it is a quasi-parabolic profile. In summary, there are many different mechanisms that can cause a smearing of energies and produce broader emission lines than what might be expected. Atoms colliding or interacting with each other can distort their energy levels, but there are also other ways that we can obtain this smearing effect. Random velocities of atoms in a gas cloud, or the motions of atoms in a rotating body that are not uniform due to thermal differences, can cause spreading out in emission lines. And external electric fields from accelerating particles can also have an effect on allowed energy values. This has been an overview of the Poynting vector and electromagnetic waves, energy flow and power, and line broadening effects we might observe in stellar atmospheres. Thank you.